This video is part 2 of Chapter 7, Repeated Measures Designs for PSY 222, Research Methods in the Psychological Sciences. Now we left off last time talking about practice effects and how to, in your design, take steps to control for those. Another type of problem that you have to think about when you use repeated measures designs is something called anticipation effects. When these types of effects, and basically, an anticipation effect is what it sounds like. When participants get a sense of what's coming and they are trying in advance to alter their behavior to meet what they expect is coming. So, for instance, if people have an expectation that they're going to learn quickly under certain conditions, that anticipation may either enhance their performance or interfere with their performance, depending on what they in fact are anticipating will occur. So participants are going to, come up with expectations. In the weighted blanket study, we had anticipation effects that we had to really think about. There's a lot of buzz and advertising about weighted blankets and how they're supposed to reduce your stress and help you relax. So people expect that, and if you have a study where you simultaneously have those kinds of expectations, but you also have people trying to guess what condition is going to come next in an experimental design, then you've got a whole mess of anticipation effects. Now, in some experimental designs, and I've seen this more in reaction time studies or studies where you have kind of rapid fire variations in conditions. So let's say you have 5 conditions and you're doing repeated measures. People can start to anticipate which condition is coming next, and that anticipation may either interfere with their performance or enhance their performance, depending on how well they guess. So those kinds of anticipation effects are different from what I was just describing in terms of just global expectations about the impact of a particular manipulation. In this case, you have a participant who's exposed to multiple conditions, and as you're transitioning from one condition to the next in a repeated measures design, they may be trying to guess which condition is coming up, and that can alter their performance. So it just becomes another one of those confounds where you're just not sure, is it their anticipation of the upcoming condition or the change in conditions, or is it the independent variable that's causing the change in performance. When you have anticipation effects and you expect them to interfere in your study, then it's recommended that you use a block randomization design so that it becomes less likely for participants to be able to form any sort of predictable pattern for what's coming. An ABBA design, they can form a response or a prediction to the changing conditions that in some ways is reinforcing for them. So you want to avoid the ABBA type manipulation and instead use a block randomization approach. Now, so far in this chapter, we've talked about complete repeated measures designs. Now we want to talk about incomplete repeated measures designs. And in the case of incomplete designs, we're having each participant is going to experience each independent variable condition only one time. And in fact, the weighted blanket study that I've been using repeatedly here as an example is an incomplete repeated measures design at its essence. So you're balancing some of the practice effects across participants, and that's essentially what we did in our study, was having different orders of conditions for different groups of participants. And that's what they mean, what your authors mean by balancing practice effects across participants. So Your authors describe a general rule for balancing out these practice effects. So you can manipulate the position in which your independent variable conditions appear, and you can do so such that each of your conditions shows up in each position with equal frequency. So there are a number of different strategies, and which strategy you take really depends on how many conditions of your independent variable you have. The more conditions you have, the more elaborate your approach will have to be. There are a couple of different techniques that you can use that your authors describe. In one case, you can create all possible orders. So every possible set of orders that you can think of, you're going to have a group of subjects that faces that order. With our weighted blanket study, there were only 2 orders that were possible, so that's what we did. Now, if we had many more conditions, then you can see how, let's say we had 4 conditions, we would have to have many more different orders such that we could expose a different group of participants to each of those orders. Now, if you have a greater number of potential conditions, you will have to do selected orders in all likelihood, because your study would end up having to have an unwieldy number of participants otherwise. And with all possible orders, as I described already, what's recommended is you have 4 or fewer independent variable conditions. Otherwise, it just gets too complex, and you have to have too many groups. And once you get beyond that 4 independent variable conditions, you end up having to raise your N to such a degree that it becomes inefficient. So if you have 2 conditions, and this is how the weighted blanket study was set up. You have 2 conditions, A and B, 2 possible orders, A, B, or B, A. And then you randomly assign half of your participants to do A. In our study, that was weighted blanket first, and then B, which was a sheet. And then the other half of the participants got the sheet first, followed by the blanket. All of the participants did a pre-test. All of the participants did a final measure after their final condition. If you have 3 conditions, you have 6 possible orders. So you can see how rapidly the number of groups of participants you have increases. So in comparison to 2 conditions where you have only 2 possible orders, when you have 3 conditions, you have 6 possible orders. So, in a study with 2 conditions, you could get away with 20 subjects per group for a total of 40 participants. When you have 6, you still have to have 20 per group minimum for your test to be valid when you're doing the statistics. So you can see how that increases your total number of N every condition that you add. With 4 conditions, you have 24 possible orders. Again, it just underscores the point. Every time you have a different order, you're going to need to increase your number of participants. When you're doing selected orders, you're going to, in some ways, it's like you're going to have enough orders that you're dealing with your practice effects, but you don't have to have so many that you have every possible sequence. There are a couple of different methods for this, and some of them are quite elaborate. A Latin squares approach is one version, and then you also have a random starting order and rotation that allows you to, you're not doing every single possible sequence, but you're doing enough that you are able to control for your practice effects. Each of your independent conditions in these selected orders approaches is going to be in the, let's say you have 4 ordinal positions. You want each IV condition to be in each ordinal position only one time. So you won't have all possible orders, but you will have enough that you've created some balancing of potential practice effects. You'll be randomly assigning participants to only one order, such that you end up with a certain set number of orders. Each participant is going to get only one order. That balances the practice effects across your different orders that you've created. And your authors provide you with this graphic, and I put it in here in the presentation to remind you to look at it in your chapter, and so that will help you to understand what they're doing in terms of creating different orders. So when you have all possible orders, it's across the rows are the different orders, and you can see how you have each ordinal position for the different conditions of the experiment. And each one of these rows creates a different order for you to assign participants to. So you would be randomly assigning participants to any one of these orders individually. Now, if we're talking 4 experimental conditions, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so 24 orders in a 4-condition experiment. You're going to randomly assign participants to each order in order to control for your practice effects. And in this particular study, they were looking at stigma associated with different kinds of conditions: gambling, schizophrenia, cancer, and a neutral control condition. That's what the letters represent. So what people were doing, they were reading vignettes describing a person who has problems with gambling, a person who has symptoms of schizophrenia, a person who has cancer, and then a neutral condition where the person isn't challenged by any of the other 3. And they present them in these different orders in order to prevent, say, reading about someone with cancer first, biases responding to the other 3, or reading about gambling first, biases responding to the other 3, and so on. So you don't have every possible order when you're using the selected orders approach. So you can see if I had to do all possible orders in a 4-condition experiment, and I needed to, get enough N to make the appropriate comparisons, I have to have way more subjects here than here. So in the Latin squares approach, you're balancing in this way. In the random starting order approach with rotation, you're starting in this way. And your authors give you a longer explanation of exactly what the rules are for Latin square versus random starting order. Now, I'm not going to go into a great deal of detail about it because the chances are low that you're going to need to use this approach. But if it turns out, say, in your senior research that you do need to use this approach, then you have the resources available to you to look up how to do them. Now, just a little bit about the Latin square approach. Each condition is going to land in each ordinal position. So if you have 4 conditions, you have position 1, position 2, position 3, position 4. And each of your conditions is going to land in each 1, 2, 3, or 4 one time. And that will be how you balance the practice effects. So each condition is going to proceed and follow every other condition, and that's how you set up the Latin square. There are lots of examples on Google when I do a search for Latin square example, and I just put that in as the search term. And it may be instructive for you to do that. It will show, lots of different examples in real type experiments, because sometimes it's one thing to read the rules of how to build a Latin square. It's another to see exactly how it played out in an actual experiment. Just remember that the goal of a Latin square is to balance potential order effects effectively. Now here's an example that I found when I did a Google image search for example of a Latin square approach. And each of the conditions is in each ordinal position one time. So A is in the first position, second, third, fourth. B is in the first position, second, third, fourth. C C is in the first position, second, third, fourth, and so on. And by doing that, you're not having every single possible order, but you are randomizing enough to represent a protection against the threat to your internal validity of the practice effects. In random order with rotation, what you're doing is generating some random orders of your conditions. So again, if you had 4 conditions, after you generate a set of random orders, and there are actually random order generators that you can use on the internet to do this for you. We used to have to look it up in tables. We don't have to do that so much anymore. Once you have your set of random orders that you've constructed, then you rotate them. So you move each the order 1 position each time. Eventually you'll have each condition appearing, just like with the Latin square, in each ordinal position 1 time. The order of the conditions isn't balanced, but what you're doing is ensuring that you have that spreading out of the position, the ordinal position of your conditions. So for example, you have the random starting order here. That's your random starting order, DACB. Then you want to do the rotation. Now you can see some patterns here where the C's are, where the A's are, where the B's are, where the D's are, and A's and C's and B's again. So you're rotating that initial randomized order. So if you have 4 conditions, you generate a random sequence of the letters, and then you rotate them around through your total participant pool. Again, you know, the goal here is to create enough randomization of your orders that you are controlling for the practice effects without having to go to that unwieldy 24 separate orders that you would have to do if you used every possible order. Now, your authors give you a brief summary of what kind of data analysis is done with repeated measures designs. As with any data analysis that you do for a study that you've conducted, you first need to do your descriptive statistics. So you start with summaries, scores that represent the data for your conditions. So you're going to report typically means with some kinds of data. If it's ordinal data, for example, you want to report medians. And we'll often do that by participant if it's a small enough sample size. Otherwise, you may, if you have groups who are exposed to different orders, like with the weighted blanket study, we actually presented in our results one table that showed the participants' means in each order, so that we could show graphically that there in fact were no differences between the 2 orders. So the descriptive statistics, what they're for, you're describing, you know, the mean and standard deviation typically is allowing your reader, when they're reading your results section, to say, okay, on average, what were the scores in the various conditions of the experiment? Then what you're going to do is statistically a similar set of analyses that you would do with random groups and independent groups designs, but the statistic will take into consideration the impact of time as a variable. As was described in the last chapter, you will be using null hypothesis testing and confidence intervals to make decisions as to whether the effects that you see are significant. I think what I will do, I've used the example of the weighted blanket study so many times with this chapter. I think I will post the link for you to their SCE presentation from Scholar Day last year, so you can see what they actually found in the study. But essentially, you're going to use the same process. You generate your descriptive statistics, means and standard deviations, and then you run a test that allows you to determine across my conditions of my independent variable, is there a meaningful difference? And what you're able to control for is the impact of time. Here's an example from your text of a repeated measures table showing you the descriptive data. So in this case, you've got means and standard deviations for different intervals. Their responses in terms of the interval length of their exposures. And the table shows the means, and then these means are what you would be comparing. So if you look at the interval length, you got 12, 24, 36, and 48. And then you can eyeball these numbers, and you can see the scores changing with the different levels. Now, since you're doing this within subjects, so subject 1, you see 13, 21, 30, and 38. Now, eventually your statistics is going to have to collapse across these participants and make some comparisons of the different interval lengths, such that you as the researcher can say interval length, that's my independent variable, that the change in the interval length is the thing that is driving the change in responding, right? As opposed to the order and the passage of time. So it may be that participant 1, it was exposed to 36 first, followed by 24, then 48, then 12. When we present it graphically, or not graphically, in a table, they're going to be reordered so that you can, as the reader, you can visualize what the researcher is actually testing. Now, one additional problem that you have to deal with in repeated measures designs is something called differential transfer. And I always found this a concept that was hard for me to understand when I was in your position as a student. Basically, in some research designs, the tasks that you are having participants do have persistent impacts on their performance, especially if it's a task where once you acquire a skill or you get a little more practiced at a skill, that becomes sort of a permanent effect, and it can persist and then impact every other condition that follows. Sometimes when you run the first version of a study, if you find you've got just way too much differential transfer, it can mean that once they're exposed to, say, condition B out of 4 conditions, once they hit B, they're done. Their performance then ceilings out, and there's no change after that. You may have to change your design in terms of the tasks that you're using, such that you can reduce the differential transfer. You may find you can't use exactly the same task, but instead a related task that addresses a similar cognitive skill, for example. But it's not so similar that you have differential transfer. So variables that are vulnerable to this kind of differential transfer effect should be tested not with a repeated measures design. You would have to test them using independent groups. You would have to randomly assign people to groups, because the differential transfer becomes a threat to the internal validity of your study. So basically, once you learn something, you can't unlearn it to be in the next condition. So if you're talking about a task that once people learn it, their learning is going to influence every other condition going forward, a repeated measures design is basically ruled out. If there's no way to reduce that, then you have to use an independent groups design or a random groups design instead. One way to find out if differential transfer is going to be an issue is to use that incomplete repeated measures design and look at the the results across conditions. And what I was describing, what we did with the weighted blanket study, that's kind of what we did. We took a look at our two orders and then we made some direct comparisons. So we compared the blanket in the first ordinal position versus the blanket in the second ordinal position, and we looked at the mean scores for the three dependent variables. What we wanted to see was that they were not different. And that's in fact what we saw, was that they were not. So that told us there wasn't differential transfer. So let's say, here's a concrete example. If we were seeing differential transfer, the people in the weighted blanket first condition would get so relaxed and they would stay relaxed, and it wouldn't matter that you took the blanket away and put the sheet on. They just stayed relaxed, right? That's not what happened. So in that case, since we had an incomplete repeated measures design, we were able to show that there was not differential transfer. So that's one way that you can detect whether that's going to be a problem for you. Differential transfer can be identified also by comparing results for the independent variable when you put it into a random groups design as well. So sometimes researchers in their research program will do both a repeated measures design of the test of the independent variable, and then they'll also do a separate study to use a random groups design. And what you're looking for is convergent findings. You're looking for the same pattern of results. What I've often seen is for researchers to start with the random groups design. It's kind of like a proof of concept test. So you randomly assign subjects to your experimental and control conditions. You find a difference, but you've used a random groups design. You'd like to be able to show in a little more sensitive test the same effect. So then you go to the repeated measures and you're able to demonstrate the same pattern. Then you have a very robust finding. Now when we're trying to get the big picture of these repeated measures designs versus our independent groups designs, it's helpful to think about pros and cons. So you've got independent groups designs or random groups design, as your authors often describe it. Some of the strengths of the independent groups designs: you don't have problems with order effects because each participant is only getting one condition. You lose fewer participants because they're participating for typically less time. In the strengths of the repeated measures design, you have perfect matching because people are their own control group. You also can reduce the number of required participants by half, typically. And that's a true advantage if you're talking about research that's difficult to recruit for. Weaknesses for independent groups designs: you may miss things, and it means that you have some sneaky individual differences that actually affect your results. So when you have groups that are not well matched, despite the fact that you've randomly assigned, that can be a threat to your internal validity. It also means you do have to recruit twice as many participants. So that's a weakness of the independent groups designs. A weakness that we've already been discussing with the repeated measures designs: you do have problems like differential transfer, practice effects, boredom, fatigue, and anticipation effects. So pros and cons both ways. I'm going to say this repeatedly for the remainder of the semester. Every method you choose has strengths and weaknesses. And that's why the multi-method approach is so, so important. And it's often forgotten, that we get kind of in a habit of using our favorite techniques as researchers. We have to sometimes step back and remind ourselves that every method has weaknesses, every method has strengths. The best research programs are going to use multiple tools to come at the phenomenon that they're interested in from more than one direction. So that concludes part 2 of chapter 7.